Hello, in this video we're going to talk about the nested interval theorem. First, what is the nested interval theorem? And then we'll go over the proof of that. So imagine you have a bunch of intervals that each one of them contains the next one. So the first interval, a1 to b1, is the largest interval. And all of these intervals must be closed. The next interval is a2 to b2, and so on. So if you have an and bn, the interval an plus 1, bn plus 1 would be inside that. It could be that some of these intervals are equal, but they would not get larger, so they would always get smaller. So then what happens is there is going to be the intersection of all of these intervals would be an interval, or it could be a single point where a is the supremum of an's and b is the infimum of bn's. So how do we articulate that formally? Suppose in equals an comma bn, which is a closed interval. Very important to make sure that the intervals are closed, and this is something I will discuss after this theorem. So this is a sequence of intervals for which in plus 1 is inside in. So it could be that in plus 1 and in are the same, but it is always in plus 1 inside in for all n. Then the intersection of these intervals is a non-empty closed interval. So it's an interval from a to b. It's a closed interval, and the lower bound of this interval, the left endpoint of the interval, is supremum of an's, and the right endpoint is infimum of bn's. Furthermore, if an minus bn approaches 0, then the intersection contains a single point. Okay, so let us go over the proof of this one. So first, we would like to prove that the intersection is in fact a comma b. If you want to show the intersection is equal to that, you have two sets and you want to show they are the same. How do we show two sets are the same? This is what you want to think about it for a second. The way we show two sets are the same is by showing that elements of each of these sets are inside the other. So elements of the left side are inside the right side, and elements of the right side are inside the left side. So let's take an element inside the intersection. So let x be inside the intersection of n equals 1 to infinity. So that means for every n, x is inside in, which means x is between an and bn. Now, since an is an increasing sequence, well, I don't even need that. So what I know is that x is greater than or equal to all of the an's. So that means by definition of supremum, supremum of an would be less than or equal to x. So x is an upper bound for an, supremum is the least upper bound, which means x is greater than or equal to supremum. Similarly, by definition of infimum, x is less than or equal to infimum of bn. So that tells us x is between a and b, or x is inside the interval from a to b. So we just showed that if you take something inside the intersection, it would be inside AB. Now let us show the other way around. In other words, if you have something inside the interval from a to b, it would be inside the intersection. So now suppose you take an element, let's call it x also, because these are really separate part of the proof. So it is okay to use the same letter. So let x be inside the interval a to b. So that means x is greater than or equal to a and less than or equal to b. Now, since a is the supremum of an, a is greater than or equal to an for all n. And since b is the infimum of bn, b b is less than or equal to bn for all n. Now combining these, we get x is greater than or equal to a, which is greater than or equal to an, less than or equal to b, which is less than or equal to bn, which means x is inside in. And this is true for all n. And that means x is inside the intersection. And therefore the intersection is in fact the same as intersection of in is the same as the interval from a to b, n equals 1 to infinity. Okay, so that proves the first part of this theorem, that this equality holds. Now, the furthermore part says if the limit of the difference of an and bn is 0, then the intersection contains a single point. So, notice that the sequence an is an increasing sequence. So, since in plus 1 is inside an plus 1 is less than or equal to an. I'm sorry, the other way around. An plus 1 is greater than or equal to an. So if I were to draw the diagram here, in is here, an, bn, in plus 1 is inside it. So an plus 1 is greater than or equal to an, and bn plus 1 is less than or equal to bn. Now, because of that, an is increasing and increasing, and bn is a decreasing sequence. Since an is an increasing sequence, by monotone convergence theorem, it would converge to its supremum. By the monotone convergence theorem, supremum of an is the same as limit of an. So that means limit of an is equal to a, because supremum of an is equal to a. And then similarly, limit of bn as n approaches infinity is equal to b. Now let's see what happens. Now by assumption, limit of an minus bn is 0 as n approaches infinity. And that means if you take limit of an, you get a. If you take limit of bn, you get b. So a minus b is 0. So that means a is equal to b. And therefore, if you take the intersection of n equals 1 to infinity, that is interval from a to itself, which is a single point a. And that's exactly what we wanted to prove. We wanted to prove that if an minus bn approaches 0, then the intersection contains a single point. And that completes the proof. And the proof of this direction started from here. So let me be a bit more, emphasize a little bit more as to what was going on here. So assume that limit of an minus bn is equal to 0 as n approaches infinity. Okay, so finally, one thing that I know and I mentioned earlier was that these intervals must be closed intervals. If you take open intervals, then this nested interval theorem is actually not valid. So here's an example. If you take the intervals 0 to 1 over n, and then you take the intersection is empty. And the reason is, if you take some positive number, then there is always some natural number n for which x is not inside 0 to 1 over n. So the intersection of 0, 1, and then 0, 1 half, and then 0, 1 third, and so on. Any x that you take here, there's always some n that x is more than 1 over n, which means the intersection of these intervals is empty, which is obviously not a non-empty closed interval. So that brings me to the end of this video. In the next video, we're going to talk about some consequences of the some consequences of the monotone convergence theorem. And if you would like to follow with with these videos, feel free to subscribe. I will see you in the next video.